speak about my published paper in Fuel last year, the theoretical reaction rate model of a chemical exothermic decomposition surface from an external gas. The paper is extensive in mathematical derivation, but I have compressed it into basic ideas in this presentation. Introduction. I will present a physical model with physical parameters. It's an analytical model and not a computational one. It's not empirical either. A new concept of co-volume is introduced. Kinetic theory is used to establish equation of state. Closed form expression for linear reaction rate is achieved. A simple formula for activation energy is also achieved. If we are interested in amount of generated gas, we need to look into geometry and porosity. And lastly, I will compare theoretical model with experimental data. Co-volume. There are three main parts to the new co-volume model. Part one is that when we measure over time, each point in a volume eventually contains information regarding every possible interaction. Part two is that the particles can be grouped together into blocks that interact equiprobably. These two parts are illustrated in the configuration space above in the figure. The colored squares are different blocks, and we see that every possible interaction between blocks is contained in the configuration space. We also see that this leads to that each colored block is represented more than once in the configuration space, which means that each particle is represented more than once also. That leads us to the third part, where we count only distinct blocks at a time, and that gives us the co-volume, where each particle is only present once, and that leaves room for blank space. Joule probabilities. The difference in block volume and co-volume produces two probabilities. First one is the interaction probability nu, which models mass change with block volume, because the interactions are modeled in blocks, as was shown in the previous slide. The second one is reaction probability pi, which models mass change in co-volume, because the entire particle must engage in the reaction. The block density d used above is modeled as the particle density given by the Lennard-Jones potential at a given temperature. If you plug in the temperature as the potential energy in the Lennard-Jones potential, you can find a radius for the particle that corresponds to that density that we call block density. This enables us to handle the molecules as particles. There are initial values for interaction and reaction probability, which is autoignition and activation energy accordingly. This can be shown with the help of the Maxwell-Boltzmann distribution. Kinetic theory and linear reaction rate for eroding decomposition surface. To find the linear reaction rate, we begin with the energy momentum conservation for a decomposition surface. The left side of the equation is the unreacted side, and the right side is the reacted side with subscript 1. Subscript V is surface and subscript L is gas. We see that the heat of reaction is stored in the unreacted side, and when released, it's transformed into velocity. We need a third equation, an energy balance that include activation energy UA. There are two parts to this equation. First one is that the surface reacts only at the ignition points, hence nu times surface mass. The second one is the portion of the gas that reacts is the reaction probability, hence pi times gas mass. To model an eroding surface, the linear reaction rate Vb must be added to the internal gas velocity to get the total kinetic energy of the gas that reacts. This kinetic energy must be equal to the activation energy needed to sustain the reaction, shown left in the equation. Combining these three equations above, you get the linear reaction rate Vb, which depend on the gas pressure P, unreacted density rho B, the heat of reaction UB, the interaction and reaction probability nu and pi. These equations change depending on the reaction type. If you have something else than eroding decomposition surface, you need to redo these equations to get a new linear reaction rate. Pressure. The complexity of pressure expression comes from solving a cubic equation, but basically it's a gas density dependence. Pressure and temperature curves for HMX. Surface pressure peaks at high gas densities. Temperature remains approximately constant for low gas densities, then drops to zero for high gas densities. For comparisons, the density of HMX is 1960 kilograms per cubic meter. Activation energy. The gas pressure and temperature is dependent on activation energy UA. This is a complicated expression, however the problem can be simplified greatly by looking at near zero gas density, in other words idle gas. The energy storage or closed vessel temperature is related to the gas temperature with a factor of 2, because only half of the released gas will kick back at the surface. With this simple step, we can derive a simple expression for the activation energy, UA, which is equal to 1/4 times square root of heat of reaction UB and energy storage UC. This expression of the activation energy is valid for both exothermic and endothermic reactions when the sign of heat reaction UB is omitted. Activation energy for hydrogen. I will attempt an example of activation energy for hydrogen reacting with oxygen to form water. The energy storage for this reaction is 120 megajoules per kilogram. The heat reaction to split hydrogen and oxygen to atoms is 218 megajoules per kilogram for hydrogen and only 31.1 megajoules per kilogram for oxygen. That means that the decomposition of hydrogen determines the activation energy to form water. Plugging this into expression for activation energy from previous slide yield 80.9 kilojoules per mole. For combustion or oxidation, overall activation energy typically ranges from 64 to 83 kilojoules per mole for high temperatures, so it fits well. Geometry and porosity. If you are interested in generated gas, we need to look at geometry and porosity, where the mass fraction μb measures the fraction of reacted material. The rate of generated gas is expressed by fraction rate and is related to the linear reaction rate Vb with a geometry factor g, that is surface over volume. When the volume is constant, the porosity phi is directly related to mass fraction μb with the initial values. The same applies for the gas density, directly related to mass fraction and the initial values. Gas density is important because it's the main input parameters to linear reaction rate Vb. Burn rate data for HMX. Lastly, I will show you an example of theoretical burn rate for HMX and explosive. HMX is a good example to verify the model due to the many orders of magnitude that data spans over. I have used literature data to establish physical parameters for the model of HMX, shown as below. These parameters completely defines the theoretical model for HMX, and you see the result in the figure to the right. The red and green line is theoretical model, where red is for low gas densities and green is for high gas densities that we usually don't see. For low gas densities, we have a pressure chamber that gives us data, and the theoretical model fits very well with the experimental data. For high densities, diamond anvil experiments are used that measure small grains of HMX. There is more uncertainty and spread in the data, but the theoretical model fits reasonably well to the experimental data. The burn rate for HMX ranges from millimeters per second to 180 meters per second, reaching up to 12.8 gigapascals. To summarize, the physical quantities that govern the reaction are both ignition temperature, activation energy, heat of reaction, block density, closed vessel temperature, gas temperature, surface density, and particle masses. If you can control these quantities, you can control the linear reaction rate. Conclusion. A fully physical model of linear reaction rate is established. Good agreement with experimental data. The parameters used in the model have physical origins. It's a fully theoretical model and not empirical. Simple expression for activation energy is achieved. For other reactions than decomposition surface, other equations of state must be considered. There is further work on other types.
All right, so hi everyone. So thank you for attending my presentation at Chem Catalyst 2026. Right. Okay, so today's I will be presenting our book entitled Engineering Synergetic Bimetallic Oxide Catalyst for Sustainable Process Intensification in Biodiesel Production. So my name is Teo from Faculty of Science and Technology, Universiti Malaysia, Sabah, Malaysia. So this work will focus on development of the mixed oxides catalyst for enhancing biodiesel production through a new critical methanol transesterification process. So the study will integrate the catalyst engineering with process intensification strategies to achieve rapid biodiesel production while reducing energy demand and improve sustainability. Okay, so before we dive into the research, please allow me to spend a minute to introduce Sabah and Universiti Malaysia Sabah, where this work was conducted. So Sabah is the second largest state in Malaysia and is located in East Malaysia on islands of Borneo, which is shared by Sarawak, Brunei, and Indonesia, Kalimantan. So Sabah is well known for its rich biodiversity, beautiful natural landscapes, and cultural diversity. So it's a home of the world's largest flower of Rafflesia, as well as the Mount Kinabalu, one of the highest mountains in Southeast Asia. So Sabah is also famous for the beautiful islands and marine biodiversity, including Simpadan Islands, one of the world's renowned diving destinations. So in addition, our Sabah is a multicultural state with more than 30 indigenous ethnic groups. The Kadazan Dusan people from the largest indigenous community and contribute greatly to Sabah's unique culture and tradition. So we warmly welcome everyone to visit Sabah in the future. Okay. Universiti Malaysia Sabah was established in 1994 and is located in Kota Kinabalu, Sabah. So it's well known as one of the tourist attractions in Sabah due to its beautiful quarters setting and eco-campus environment. So some of iconic landmarks in the UMS include the clock towers, okay, the Pink Malls Aquarium and Marine Museum, so as well as the outdoor education centers, which is popular attraction among the visitor and student. So currently, UMS consists of 10 faculties offering a wide range of undergraduate and postgraduate programs. So I'm affiliated with the faculties of Science and Technology, where my research focus on the catalysis and renewable energy. So, okay, let's move to the topic today. So, okay, so today the world faces the two major challenges, the increasing the energy demand and environmental sustainability, global sustainability. So global energy consumption is continues to rise due to the population growth and industrial development. Currently, most of our energy still come from fossil fuels, okay? So such as petroleum oil, natural gas, and coal. However, so these resources are finite and non-renewable. In addition, the combustions of fossil fuels release large amounts of carbon dioxide and other greenhouse gases, contributing to climate change and environment pollution. But at the same time, the fluctuations in fuel prices and concerns over long-term energy security have created an urgent need for sustainable and renewable energy alternative. So therefore, significant research efforts has been devoted to developing cleaner fuels that can reduce our dependence on fossil resources while minimizing the environment impact. So one promising solution is to reduce our dependence on fossil fuel is biodiesel, which is derived from renewable biological resources. So biodiesel has attracted considerable attention because it offers several important advantages over conventional petroleum diesel. So first is a renewable and sustainable fuel that can be produced from various biomass resources. So second, the biodiesel posts physical and chemical properties that is very similar to the petroleum diesel, allowing it to be used in existing diesel engine with a little or no modification. So from environment perspective, biodiesel is biodegradable, non-toxic, and contain very low level of sulfur aromatic compound. So as a result, its combustion generally produce lower emission and cause less environment harm compared to fossil-based diesel fuel. So because of these advantages, so biodiesel have emerged as one of the most promising alternative fuels for improving energy security while supporting sustainable development. So among the various feedstock available for biodiesel production, our study focused on the jatropha crude oil, a non-edible oil source with significant potentials for sustainable biodiesel production. So look at this slide. An equally important factor in the biodiesel production is the selections of the suitable feedstock. So in this study, we selected jatropha cookers, or locally they're known in Malaysia as jarapaga. So jatropha is considered a promising biodiesel feedstock because it is non-edible plants and therefore does not compete with food resources. So in addition, it is a fast-growing crop with high oil content and can be cultivated in a right and semi-arid region with relatively low agriculture input. So these advantages that make jatropha a sustainable and attractive feedstock for the biodiesel production, and therefore it was chosen for this study. So after selecting the feedstock, the next challenge is how to efficiently convert the oil into biodiesel. Okay, so this brings us to the transfer process used in our work here, right? So after selecting the feedstock, the next challenge is we have to convert the oil into biodiesel. Also, one of the well-known approach is the supercritical methanol process, also known as Saka method, which is first introduced in 2001. So the main advantage of this process is that biodiesel can be produced without using a catalyst, while the transfer reactions can be completed within a relatively short period of time. However, the process also has several limitations, so it requires very high operating temperatures, typically around 300 degrees Celsius, together with high pressure conditions. In addition, the reaction still require a considerable processing time. So as a result, the process consume a large amount of energy, so leads to the high operating cost, which is limit its practical application. So therefore, there is a need to improve the process by reducing the reaction temperature, shortening the reaction time while maintaining the high biodiesel production efficiency. So to address the limitation of supercritical methanol process, we developed a serum calcium mixed oxide catalyst and evaluated its performance for biodiesel production under near critical methanol conditions. So the catalyst was synthesized using a simple core precipitation method. The metal precursor solution containing the serum and the calcium salts will mix with the alkaline precipitating agents to form the catalytic precursor. So the resulting precipitate will then dry, calcine, and subsequently characterized to determine its physical chemical properties. So for the catalyst reaction, the unrefined jet crude oils were reacted with the methanol in the presence of synthesized catalyst using a high pressure batch reactor. So the transesterification reaction was carried out under near critical methanol condition. So after the reaction, the product was separated into biodiesel and glycerol phases, and the biodiesel composition were analyzed using gas chromatography technique. Okay, so using this methodology, we investigated the relationship between the catalyst properties and the biodiesel production performance. So let us first examine the physicochemical properties of the synthesized mixed oxide catalyst. So the SRD profile show on the left of confirm the successful formations of crystalline silver oxide and calcium oxide phases in all synthesized catalysts. So the characteristic diffraction peaks can clearly assign to the fluoride structures of silver oxide and the cubic structures of the calcium oxide. So an interesting observation is the change in crystallite size with the catalyst composition. The interaction between the serum and these calcium species influences crystal growth, indicating the formation of a mixed metal oxide system rather than a simple physical mix of the two components. So as shown in the table and figures, the catalyst composition also affects the surface area and the crystalline size. So generally, increasing the calcium oxide content will lead to the larger crystalline sizes and reduce the BET surface area. So this result demonstrate that the physical chemical properties of a catalyst can be turned by adjusting the serums to calcium ratio, which is expected to influence the catalytic performance during the biodiesel production. So besides surface area and the crystalline size, so another important properties for transesterification catalyst is the basicity. So to evaluate the basic strength of the synthesized catalyst, the carbon dioxide temperature program desorption analysis will perform. So the result will show that here, the mixed metal oxide catalyst exhibits a stronger basic size compared with the single metal oxide catalyst. So as shown in the TBD profile here, so the desorption of peaks of the mixed metal catalyst appear at higher temperature to indicate that the presence of a stronger basic size. So these basic size are important because they serve as active centers for transesterification reaction. So the enhancement in basicities can be attributed to the interaction between the serum and the calcium species within the mixed metal oxide structure. So these synergetic effects that strengthens the surface basic size and increase the overall catalytic basicity. So among these catalyst study, the basicity follow the orders of this arrangement This arrangement indicates that the catalyst composition play a crucial role in determining the catalytic properties. So these findings suggest that the incorporation of a serum in the calcium oxide system can be effectively improve catalyst specificity, which is expected to enhance the biodiesel production performance. So next, we examine the morphology of the synthesized catalyst using scanning electron microscopy. So as shown in these images, the morphology of the catalyst changes significantly with the serum to calcium ratio. So the pure serum oxide show particles with the irregular shapes and non-uniform size distribution. So after introduce a serum oxide, so the changes very significant in the particles morphology can be observed. So indicates that the catalyst composition influence particle growth and aggregation during the synthesis process. So what interesting here is the serums mix serum calcium mixed oxide will show a more homogeneous particles distribution as compared with the other composition, okay, suggesting a better interaction between the serum and the calcium oxide phases. However, when the calcium content is further increased, the particle agglomeration become more pronounced. So this observation again confirm that the catalyst morphology can be tolerated by adjusting the serums to calcium ratio, which may subsequently influence the catalytic performance. So after understanding the catalytic properties, we next evaluated the catalytic performance of the mixed oxide catalyst for biodiesel production under near critical methanol condition. So this figure show the effects of the serums to calcium ratio on biodiesel production and the catalyst basicity. So as can be seen, the biodiesel production increased significantly after introducing the calcium into the catalyst system. So among all the composition, investigated the serums to calcium 1:1. We achieved the higher biodiesel yield for approximately 58%, which corresponds to the higher catalyst specificity. So these results suggest that catalyst specificity play a crucial role in promoting the transesterification reaction. So in general, this higher specificity provides more active site for conversion of triglyceride into biodiesel. So however, as we can see here, when the calcium content was further increased, a decline in biodiesel yields were observed. So despite the presence of the strong basic site, so this may be attributed to the excessive the calcium loadings, which may negatively affect the catalyst properties and accessibility of active site. So after identify the optimum catalyst composition, we investigate the effects of methanol to oil molar ratio on biodiesel production. So as shown in the figure, so the biodiesel yield increased significantly as the methanol to oil ratio was increased from 9:1 to 24.1. This is because the high amounts of methanol will promote the transesteric reaction and shift the reaction equilibrium towards the biodiesel formation. Okay. So when the temperature increase, sorry, right. Yeah. So among this condition, condition investigation, the higher biodiesel yields approximately 83% can be achieved with the methanol to oil ratio of 24. So using the mixed oxide catalyst. Okay. So however, the increased contents of methanol were resulted in decrease of biodiesel yield due to excessive methanol. It dilutes the reactant and the reaction intermediate and reducing the effectiveness of the transesterification process. Okay, so next is we investigated the effects of the reaction temperatures on biodiesel production. So as shown in the figure, So biodiesel yield increased significantly with increased reaction temperatures for all the catalyst system. So at the lower temperatures, in between 180 to 220 Celsius, the biodiesel yield remained relatively very low because the transfer reaction proceeds slowly. So when the temperature was increased, the biodiesel yield improved substantially. The highest biodiesel yield will approximately 79% were achieved at the 260 Celsius. Okay, by using the mixed metal oxide, indicate that this temperature provides the optimum reaction condition. So the improvement in the biodiesel production can be attributed to the enhanced reaction rate and improve the miscibility between the methanol and oil at the elevated temperatures, which facilitate the transesterification process. So therefore, 260 Celsius was selected as the optimal reaction temperature for subsequent study. So we investigated the effects of reaction time on the biodiesel production by using the same mixed oxide catalyst. So as shown in the figures, the biodiesel yield increased rapidly with increased the reaction time. So at the same temperature, so the biodiesel yield will react approximately 79% within only 10 minutes. So demonstrating the effectiveness of the catalyst under new critical methanol condition. So if further increasing the reaction times to 20 minutes resulted in the highest biodiesel yield for approximately 93%, indicating that the transesterification reaction was nearly completed within this period. But in contrast, at the temperatures of 220 Celsius, a much longer reaction time was required to achieve a similar level of conversion. So this suggests that the higher reaction temperature will significantly accelerate the reaction rate and improve the conversion efficiency. So this result demonstrate that the combination of new critical methanol condition with the mixed oxide catalyst enable rapid biodiesel production with high conversion efficiency. So the final reaction parameter investigated was catalyst loading. So as shown in the figure, the biodiesel yield will increase significantly as the catalyst loading was increased from 0.2 to 1%. So this improvement can be attributed to the greater numbers of available active site, which promotes the transesterification reaction. So the highest biodiesel yield of approximately 93% was achieved at the catalyst loading of 1%, which indicates this amount provided sufficient active sites for efficient biodiesel production. So however, with further increasing the catalyst loading beyond 1% resulted in a decrease in biodiesel yield. So this may due to increase in the viscosities of the reaction mixture, and which reduce the mass transfer and limit the interaction between the reactants and the catalyst active site. So therefore, a catalyst loading with 1% will identify as an optimum condition for the biodiesel production using this mixed oxide catalyst. So beside of the catalytic activity, the resistance of the catalyst towards the water contamination is an important consideration for practical biodiesel production. So therefore, we investigate the effects of water content on biodiesel yield and compare the performance of the mixed oxide catalyst with the conventional homogeneous catalyst, which is sodium hydroxide. So as shown in the figures of this, the mixed oxide catalyst maintained a biodiesel yield above 90% when the water content was increased up to 3%. So this indicates that the catalyst poses good water tolerance and strong resistance toward moisture deactivation. In contrast, when we see it on the sodium hydroxide catalyst, was highly sensitive to water contaminations. So even at only 1% water contents, a significant reductions in biodiesel use were observed. So even a further increase in water's content eventually reduced the biodiesel yield for both systems. So the mixed oxide catalyst consistently outperformed the conventional homogeneous catalyst. So this result demonstrates the superior water resistance of the mixed cerium calcium oxide catalyst, highlighting its potentials for practical biodiesel production using feedstock that may contain moisture impurities. So beside the water tolerance, we also evaluated the resistance of catalysts towards the free fatty acids, which are commonly present in low quality and unrefined feedstock. So as shown in the figures, the mixed oxide catalyst maintains a high biodiesel yield. So even when the oleic acid content was increased, so this catalyst was able to retain the biodiesel yield above 80%, even at 10% of the free fatty acid contamination. But in contrast to the homogeneous catalyst system, was highly sensitive to the presence of free fatty acids. A significant reduction in the biodiesel yield were observed as free fatty acid content increased. So this behavior is mainly attributed to the reaction between the free fatty acid and the homogeneous catalyst, so which leads to soap formation, consequently reduce the transesterification efficiency. So therefore, this mixed oxide catalyst will show a very excellent acid tolerance and is more suitable for processing low quality feedstock containing high level of free fatty acid. So for practical applications, so the catalyst stability and the reusability are equally important as catalytic activity. So therefore, a reusability of the mixed oxide catalyst was evaluated through the multiple consecutive reaction cycles under the optimized reaction condition. So as shown in the graph, the catalyst maintains a biodiesel yield above 80% even after the eight consecutive cycles, indicating good catalytic stability and durability throughout the reaction process. So to further investigate the catalyst stability, the leaching analysis were conducted. The results show only a very low concentrations of the dissolved matter species in the biodiesel product, so indicating minimal metal leaching during the reaction. So this finding will suggest that the strong interaction between the cerium oxide and the calcium oxide will help stabilize the catalyst structure near the critical methanol condition. So the photograph here on the right will further demonstrate that's the effectiveness of the catalyst, where the clear biodiesel phase was observed, indicating successful biodiesel production with minimal contamination. Okay. So overall, the mixed oxide catalyst will show excellent reusability, good structure stability, and low metal leaching, so highlighting its potentials for long-term biodiesel production application. Okay, so to compare to evaluate the competitiveness of the developed catalyst, we compare its performance with the several previous reported calcium oxide-based catalysts for biodiesel production. So as shown in the table, most reported catalyst system require relative high catalyst loading, long reaction time, or multiple hours of operations to achieve high biodiesel yield. In contrast, that the cerium calcium mixed oxide catalyst developed in this study achieved a biodiesel yield of approximately 93% using only 1% of catalyst within 20 minutes under near critical methanol condition. So even some catalysts reported slightly higher biodiesel yield, So they generally require much more longer reaction times and more severe reaction operating condition. So this result demonstrate that the mixed oxide offers a very good balance between the catalyst activity, reaction efficiency, and process intensification. So therefore, the combination of a synergetic mixed metal oxide catalyst and near critical methanol conditions provide an efficient, very effective strategy for rapid and sustainable biodiesel production. So, to conclude this, a series of the cerium oxide, calcium oxide mixed metal catalysts were successfully synthesized and evaluates for the biodiesel production from the unrefined geothermal crude oils under the near critical methanol condition. So the incorporation of the metal oxide, mixed metal oxide generated a synergetic effect that enhance the catalyst stability and catalyst performance among the catalyst catalyst performance among the synthesized catalyst. So so among the catalyst investigated, the serums to the calcium mixed oxide with a ratio 1:1 show a base performance due to its favorable physical chemical properties and strong basic side. So with the under the optimized reaction condition, the biodiesel use of approximately 93% were achieved at the methanol to oil ratio of 18, a catalyst loading of 100%, and the reaction time of only 28 minutes. So in addition, the catalyst demonstrated excellent resistance towards water and free fatty acids together.
Well, I am thankful to the organizers for giving me the opportunities to present my views over here. My title of the presentation is Blockchain-Driven Transparency and Sustainability in Chemical and Process Industry Supply Chains. So this is what the outline of the presentation will go with: the introduction, chemical supply chain challenges, sustainability and transparency in the process industries, blockchain technology fundamentals, what is IoT and smart contract integration, sustainability monitoring and ESG compliance, industry applications and some case studies, benefits and challenges, future research direction, and at last we will have some conclusions with the discussions. So let us start with the introduction. Why we need a transparency in today's date and why we are looking towards the sustainability. Nowadays, a lot of people are talking about the word sustainability, right? So why it is important? Basically, chemical and process industries are fundamental to global economic development and support sectors such as energy, pharmaceuticals, agriculturals, polymers, and specialty chemicals. Modern industries are increasingly expected to balance economic growth, environmental responsibility, and social accountability. So increasing concerns related to carbon emissions, resolution utilization, waste management, regulatory compliance, and supply chain transparency are reshaping the future of chemical process industries. So ensuring the transparency in raw material sourcing, manufacturing processes, product quality, and environmental performance has become essential for building stakeholders' trust in achieving sustainable industry operations. So digital technologies are emerging as key enablers for creating sustainable, transparent, and resilient industrial ecosystems. So basically, when we go towards any part of industry, not restricted to the part of chemical industry, nowadays people are facing so many trouble regarding the maintenance of their environment, their ecosystem, their data set, and their stakeholders. So everything should be on the point. Point means it should be on the hand. Immediately it should be given to the customers. Immediate help should be developed. And everything should be in a very fast and rapid manner. So because time is very important nowadays for each and every individual. So basis on that, the industries are evolving drastically. So evolution of industry system from industry 1.0 to industry 6.0. Say for example, when we have the technologies of steam power and mechanical systems, mechanizations of productions. Then industry 2.0, it came with electricity, assembly lines, and mass production and productivity started. Later on, it came with the Industry 3.0, where computers, electronics, and automation came. Process automation and efficiency was the primary focus in that part. Later on, we came with Industry 4.0, where IoT, introduction of AI, big data, cloud computing, and blockchain came in that part. Smart and connected manufacturing was the primary focus, because from that part, the smart manufacturing process was started since from Industry 4.0. In the era of Industry 5.0, human-machine collaboration, sustainable technologies are the key technologies which came with the development or the era of Industry 5.0. And human-centric and sustainable production was the primary focus. And now we are running with the era of Industry 6.0, where cognitive AI is there, digital twin is there, Web 3.0 is there, and quantum technologies are there with us. So in this, the primary focus is autonomous, intelligent, and sustainable industrial ecosystems. So basically, the evolution of industrial system reflect a shift from mechanized production to intelligent, interconnected, and sustainable ecosystems where data, automation, and trust are critically enablers of industrial transformation. Among the enabling technologies of Industry 4.0, blockchain has emerged as a powerful for establishing trust, transparency, and accountability across modern chemical and process industry supply chains. So, why we are looking towards all these industries? We must have the curiosity in the mind that why we are talking about the backdated industry and why today what it is going on, that how rapidly the transformation came. That is what we need to look towards, right? So for that, we have also challenges in traditional chemical supply chains, fragmented information system, limited end-to-end traceability, lack of real-time monitoring. This is very, very important when we personally meet the industry people. They do talk about that real-time monitoring is very essential for us. Regulatory and compliance are also the challenges for them. Information asymmetric and trust issue. This is very fundamental thing and which is widely solved with this technology that I'm going to talk about today. And data integrity and security risk. So supply chain, basically, when we start with raw material, chemical processing, manufacturing plant, it goes to storage, logistic, distribution, and finally it goes to the customer. So data, limited visibility, manual verification is not possible, delayed reporting always happens, and then trust is going to vanish with the customers. So traditional chemical supply chains often suffer from fragmented data, limited traceability, and inadequate transparency, making sustainable and compliant operations increasingly difficult. Now, sustainability and transparency in modern process industry. How it is? Modern chemical and process industry must balance economic growth, environmental responsibility, and social accountability while maintaining complete supply chain transparency. Well, we talk about environmental sustainability, social responsibility, and these are the three different things. So there, carbon emission reduction, worker health and safety, cost optimization, energy efficient, ethical sourcing in social responsibility, and operational efficiency with economic sustainability. So these are the three comparisons of ESE, that is economical sustainability, social responsibility, and economic sustainability. Basically, transparent supply chains depend on end-to-end traceability of raw materials, real-time visibility of production process, continuous quality monitoring, environmental performance assessment, and robust compliance verification mechanism. So this is how the modern industries are maintaining their sustainability and transparency with the different processes. Now I come to the point where I am going to talk about why blockchain. What is the role of the blockchain in this industry and why it is going to be so emerging and so helpful for certain industries. So blockchain technology is basically building a trust in the industrial ecosystem. Now the question arises, madam, what is a blockchain? What you are talking about as in trust and for the industrial ecosystems. Basically, it is nothing but it is a ledger. This technology was evolved by Satoshi Nakamoto in 2013-14 as a first Bitcoin, which is a cryptocurrency, right? This technology was developed for the purpose of finance. It is yet not completely developed for any type of industry, but yes, it is going on under the different process with the different types of industry, that different blockchain platforms are now evolving and coming with the help for the industry. So blockchain is nothing but it is a digital ledger where we can open an account without any papers, without any signatures. Yes, but we do have a signature which is supported by cryptography, means it is secured with cryptographic algorithms and the logics. So here, it is a decentralized, immutable digital ledger that enables secure, transparent, and tamper-resistant recording of transactions across a distributed network. So what are the key characteristics of this blockchain technology? Number one, it is immutability, which records cannot be modified once validated and stored. Second is decentralization. Now, when we come to the blockchain, actually, there are many types of blockchain. So it is a public blockchain and it is a private blockchain. Those who are having public blockchain, it is 100% transparent. When we deal with a private blockchain, it is 70% and 30% ratio in the form of transparency. But the people, those who want to deploy everything with the industrial ecosystem, they are working with the part and evolving the part of public blockchain. So, transparency. Authorized stakeholders can access and verify transaction history. Anyone, even if I don't have an account, then also I can verify that which type of transactions are going on without having also an account, right? Security. Cryptographic mechanisms protect data integrity and authenticity. Traceability. Every transaction can be tracked from origin to destination. Smart contracts, automated executions of predefined business rules and agreements. Okay, so how this blockchain is developing the trust? Basically, traditional database and blockchain. So what is having the traditional? All of we are knowing that when we go with the traditional part of the data set, we are storing our data set with cloud platforms, right? Many of the cloud platforms are charging high cost of energy, and they are also many times it is not remaining secure and transparent also. So this is called the centralized control system, and blockchain is having distributed network where the data is stored very securely, transparently, and less efficient energy cost also. Vulnerable to data manipulation, tamper resistant records in blockchain, limited visibility of the data in traditional database, where here the shared transparency, anyone can see the data but the condition is if I do have a password for that particular ledger. Manual verification, automated validation, single point of failure. Here it is a high resilience of failure because it is not dependent on one authority. By providing secure, transparent, immutable records, blockchain enhances traceability, promotes trusted collaboration, supports regulatory compliance, improves sustainability reporting, and strengthens stakeholder confidence throughout the supply chain. So basically, supplier will go with the part of manufacturer, then logistic, then distributor, and then the customer. And this is how the blockchain technology store everything with the part of customer and deal. Now, what are the core components and architecture of this blockchain? Basically, how the blockchain works, that is what from this I want to explain you all. First of all, the transaction is initiated by one party. If suppose I am and want to open an account with the blockchain, any of the blockchain, nowadays there are more than 500 to 700 blockchains, and still this is going to evolve more and more in the coming near future. So transaction get initiated, then it gets verified, then it is going to be stored with the block, and then ultimately This is where the transaction got verified. Hello, am I audible?
Yes, Shukla, you're audible, but the slide is not up yet. Can you show the slide, please?
Oh, just. I will share it once. Is it visible? Ma'am?
Yes, Dr. Shukla, you can continue.
Okay. Yes, so I was actually explaining the core components and architecture from this slide for a blockchain that I will repeat once again as my slides were not visible. So transaction get initiated, then it get verified, then it will go to the block. And here the means go to the block means block will be created after the transaction get verification. Then that block will go towards the part of consensus validation. Then consensus validation will be finally, once it is validated, it will be added towards the block, and then entire blockchain will be with the among entire network. So what is this role of entire all these components? Transaction, verification, block created, consensus validation, block added, and finally shared across the network. So stored transaction records, timestamp, and other relevant data. Unique digital fingerprint of each block that ensures data integrity. So say for example, this is 1 block, 2 block, 3 block, and 4 block. There are many blocks, but how it get? Your data will come, your timestamp will come, then hash will be generated. It is related with the previous hash. So one block is created in this way. After that, all these blocks will relay upon a smart contract. That what are the execution features need to be highlighted. Smart contract is nothing but it is a digital code which provides the security towards our entire ecosystem of the blockchain. So what is consensus mechanism? That validates transaction and ensures agreement among authorized participants. What is a distributed ledger? Share and synchronized ledger maintained by all participants. Smart contract is self-executing digital agreements that automate business rules and ensure their compliance. So this is how the smart contract will provide the security which will protect the data using cryptography and advanced security mechanisms. Traceability. So it enables end-to-end tracking of every transaction. Transparency, which provides visibility and access to authorized stakeholders. Automation, which reduces manual process through smart contracts. And trust creates a single source of truth for all participants. So basically, blockchain combines distributed ledgers, cryptographic security, consensus mechanisms, and smart contracts to create a trusted and transparent digital ecosystem. So these are the main core components for the blockchain, and it is shown. Now, blockchain enables supply chain management because, as I mentioned in the architecture part, end-to-end traceability is there, tracks raw materials, products, and transactions throughout the supply chain lifecycle. Secure and transparent data sharing provides a shared immutable ledger that enables trusted collaboration among all the stakeholders. What is automation and compliance for this industry? It automates verification process through smart contracts, supports regulatory compliance with tamper-resistant records. Trust, sustainability, and efficiency. Enhances stakeholders' trust, improves the sustainability reporting, and reduces operational risk and inefficiencies. Blockchain transforms fragmented supply chains into connected digital ecosystem by providing a single source of truth for all the stakeholders. Now, what are smart contracts for automated verification and compliance? So smart contract is basically supplier will verify all the approved suppliers before material procurement, right? Quality compliance automatically validate product specification and quality standard. Environmental compliance monitor emissions and resource consumptions against predefined thresholds. Automated reporting will generate immutable records for audits and regulatory inspections. So smart contract will flow in this way. Raw material will be delivered, quality parameters will be checked, and smart contract finally gets verified. If it is approved, the record will be noted down in the blockchain. If it is rejected, then there will be alert and corrective action will be given to the person who is deploying the smart contract. So what are the industry benefits? Which will reduce the manual intervention for the data, faster compliance and verification, real-time decision making, improved data integrity, lower operational cost, and enhance stakeholder confidence. So this is how chemical industry, if the recorded emission level exceeds the regularity thresholds, generates an alert, records the event on blockchain, and initiate corrective action procedures immediately. So this is how it is important for the chemical industry. So smart contract transforms compliance from a periodic manual activity into continuous automated and transparent process. So this is how the three things are very important: automation in the industry, transparency in the industry, and compliance in the industry. And that is why the trust will be generated in this form of operations. Okay, I hope my slides are visible, right? Is my slides visible?
Yes, Dr. Shukla, is it visible?
Okay, sorry to ask you, but as in between it was not set. IoT and blockchain integration. So now I am integrating two technologies. So IoT, we can also integrate IIoT. This is Internet of Things, and IIoT is Industrial Internet of Things. We can have many combinations with this technology though. So IoT sensors continuously collect real-time operational environmental data from industrial process. Blockchain securely records and stores sensor-generated data in an immutable and distributed nature. Smart contracts automatically verify process conditions and trigger predefined actions when compliance thresholds are met. Real-time dashboards provide visibility into production performance, resource utilization, and environmental impact. Critical parameters such as temperature, pressure, humidity, energy, consumption, and emission can be continuously monitored. The integration ensures regulatory compliance and informed decision-making across the supply chain. So how this real-time monitoring and traceability will come to this industry? So basically continue monitoring data, tracking the process of parameters, equipment performance, and environmental conditions. End-to-end traceability means tracks the materials, products, transactions from raw materials, sourcing to end customer delivery. So supply chain visibility provides stakeholders with instant access to trusted and verified operational data. Protective risk management, data-driven decision-making, and immutable record keeping. So basically, if I have my IoT sensors with my industry, I can directly connect that sensors to this raw material. So raw material will be connected with this IoT sensors. Then chemical process will be also connected with the IoT sensors. Manufacturing will be also connected with that. So all the 6 parameters will be collected. Now I will connect this IoT sensors through my smart contract to the blockchain technology using the development of different or as per the requirement logic. So basically it will improve product quality, enhance supply chain transparency, faster issue identification and resolution, better regularity, reduce operational risk, and increase stakeholders' confidence. So this is how real-time monitoring happens in this industry. Sustainability monitoring in environmental social governance compliance. So continuous monitoring of carbon emissions, energy consumption, and water utilization. Real-time assessment of environmental and social governance performance. Blockchain ensures secure, transparent, and tamper-proof records. Smart contract enable automated compliance verification. Enhanced traceability support responsible sourcing and supply chain accountability. Trusted sustainability data improves regulatory compliance, stakeholder confidence, and ESG reporting. So now carbon footprint, which is now very emerging, tracking and environmental performance assessment. Continuous monitoring of carbon emission across production, transportation, and distributed activities. real-time tracking of energy consumption, water usage, and resource utilization. Blockchain provides immutable records of environmental performance data. IoT sensors enable accurate measurements of emissions and operational parameters. Smart contracts support automatic verification of environmental compliance standards. And finally, transparent reporting helps organizations achieve these ESG goals and sustainability commitments through this technology by combining two technology. This is what I am telling, IoT and blockchain. So what are industrial applications in this sustainable chemical manufacturing? If your industry is connected with IoT, and then the sensors continuously monitor this process parameter, energy consumption, water usage, and emission in real time. Blockchain securely records operational environmental data and ensuring transparency and data integrity. So real-time tracking of carbon emissions and resource utilization supports sustainable manufacturing practices. Transparent ESG reporting enables reliable sustainability assessment and audit readiness. Enhanced traceability and accountability improve stakeholders' confidence across the supply chain. And this is how the efficiency and reduced environmental impact contribute to the greener and more resilient manufacturing operations. So how this catalyst lifecycle management is there through this technology. So first of all, we will go with the part of blockchain where we have to end-to-end trace the catalyst lifecycle activities, then need to connect with the IoT sensors, continuously monitoring this catalyst performance and operation conditions. The smart contract automate catalyst regeneration and replacement of the decisions. Catalyst regeneration, reuse, and disposable activities are securely recorded. Immutable lifecycle records support compliance and sustainability reporting. Optimized catalyst utilization reduce waste, cost, and environmental impact. Say, for example, if petrochemical plant tracks the catalyst uses, efficiency, regeneration, and recycling through blockchain and IoT, improving catalyst utilization, reducing waste, and ensuring regulatory compliance. So this is how the cycle it is: deployment, performance monitoring, regeneration, resource recycling, and sustainability. So what are the benefits and challenges and future direction? So the benefits are: enhances end-to-end traceability, real-time visibility, and stakeholder trust across the entire chemical supply chain, enable automated compliance verification, trusted sustainability reporting, and improved resource efficiency for sustainable operations. Challenges are scalability, integration with legacy industrial systems, and high implementation cost can hinder large-scale blockchain adoption. So data privacy concerns, lack of standardized framework, and evolving regulatory requirements remain key barriers to implementation. Future direction: integration of AI, blockchain, and digital twin will enable predictive sustainability analytics, intelligent decision-making, and autonomous industrial operation. Industry 6.0, Web 3.0 ecosystem, circular economy practices, and quantum-safe blockchain technology will drive the next generation of secure, sustainable, and resilient supply chains. So key takeaways and conclusions. So blockchain is transparent, traceable, and trust-generated. IoT-driven real-time monitoring improves visibility of operational and environmental sustainability parameters. Smart contracts will verify and make the decision accuracy. Blockchain-based ESG monitoring supports carbon footprint taking and sustainable manufacturing practices. Industrial applications such as sustainable manufacturing, catalyst lifecycle management demonstrate significant and operational environmental benefits. The convergence of blockchain, IoT, AI, digital twin, and Industry 6.0 will drive the next generation of intelligent, resilient industrial ecosystem. So basically, blockchain is an emerging key enabler, transparent, traceable, sustainable chemical supply chains, transforming traditional industry operation into intelligent, data-driven, and environmentally responsible ecosystem. So these are my references that I have used to prepare this presentation. So thank you, one and all. Present over here.